Hello and welcome back. Now we want to talk a bit more about what we mean by learning from data. So we'll talk a bit about data quality, correlation versus causation, features and so on. So in general we have the very high level approach to machine learning. In a nutshell, we have some sort of data. It could be, for example, images or text or tabular data. And then we have our machine learning or AI algorithm, and poof, out comes a prediction. That could be a classification, a regression or some other task. And then there are two ways we could go about it. Either we have our data, like the raw data or the tabular data, and go via the deep learning approach, and that means that it's sort of end-to-end. Right? We put the raw data in and give it to the machine learning algorithm, and out comes our prediction. Or this is more what we call traditional machine learning. We have a human expert that is then creating handcrafted features. It's called feature engineering, and that is fed to, shall we say, traditional machine learning algorithm, and out comes our prediction. So how do we do this as feature engineering? That means that some human expert designs variable based on domain expertise. That can be very valuable, in particular if we don't have large data sets, because then we really need to make the most of the data that we have. And then we need to select which features are actually useful. That means we have a high correlation with the label. That means the true outcome, and a low correlation with other features. So ideally we want to have features that contribute new information and are very relevant to what we want to predict. So how can we measure this? For example, there are a number of ways how we can do this. One is feature importance. Like we can take one feature, shuffle all the variables. That breaks the connection between the feature, but we retain the number of input variables, train the model and observe how much the performance decreases. And for features that are very relevant, we expect that doing so will decrease the performance a lot, and features that don't really do much for our model don't have much of an effect here. We could also do an approach based on Shapley values, right? And this comes from game theory, and the core idea here is that sort of features are a team. Let's imagine a football team, right? So each player can play on their own, but each player has some sort of importance, and the job of the trainer, of the coach, is to select a team that in combination with all of these players has the best performance, right? But we still, and this is where these Shapley values come in, we need some sort of way of identifying the value of each player within a team in combination with other players. So essentially we can borrow from this and use Shapley values to assign a metric essentially that quantifies how valuable a given feature is in a team of other features. We could also select features based on the L1 norm. So if you apply this regularization technique, features that are not very relevant will be sort of squeezed out. The assumptions when we want to learn from data are of course quite severe, because we need the data to be representative of what we want to learn. Right? If we have data and it's not related to the task that we want to learn, there's very little machine learning algorithm can do about it. We also typically assume that the data are correct. That means that there is no bias in the data, or the data have high quality. Right? We also need features that describe what we want to learn. The variables need to be relevant. Because in the end, the machine learning algorithm exploits the correlation between all those variables or the features and the true value, the label. We can have linear correlations. These are easy to understand for us humans typically, but we can also have nonlinear and higher order correlations. So what do we mean by this? The Pearson correlation, the linear correlation, is defined by the covariance of the variables. And covariance means, like, if we change one variable, x for example, how does y, the other variable, co-vary or change in the same way? Like, how does x change if y changes and vice versa? And this is what we can see on the top row, right? So if there's zero Pearson correlation or linear correlation, you have a blob, and x and y behave independently, and the extremes are +1 and -1. Right? So if you change x, y changes by the same amount or in the negative direction, and the weaker this is between 0 and 1, the more fuzzy, shall we say, this becomes. However, this Pearson correlation is maybe easy to understand for us humans if we plot data as such a scatter plot against each other, but it doesn't capture more complex behavior. So for example, in the second row, you can see that these are clearly all different, but they have a Pearson correlation of exactly 1 or exactly -1, but you can see visually that these data points behave very differently. And the third row is even worse, right? All of those have a Pearson correlation coefficient of 0, but you can clearly see that all of these data points are correlated in some way and higher order linear way. So if you rely on correlations, right, most people are only thinking of the Pearson correlation. You can see that Dragon's Spear here because that only measures linear correlation and doesn't help you with more complex relationships. And there's an issue, refines the correlation, just is it a good correlation, right? Remember that machine learning exploit the correlations, but do they actually help? Correlation does not imply causation. So for example, the correlation can be meaningless or random, and this is what we call spurious correlation. But the correlation is there, and if it's in our data with our feature variables, right, the machine learning algorithm will learn those wrong relationships. And there's one instructive example. Here we have the number of sociology PhDs versus non-commercial space launches, and you can see from that time series these variables are highly correlated. Over many years they exhibit the same behavior, but obviously the number of sociology doctorates versus non-commercial space launches have nothing to do with each other. And that may be obvious if you know now the variable names, but you will have the same behavior in many data sets, and it's not so obvious to discriminate between good and spurious correlations. So what you, for example, often do is when you decide which features to include in your machine learning model based on your domain knowledge, you see that many people include many variables and then use feature selection methods, like for example, the one that we discussed previously, to remove all those unnecessary features automatically. However, this approach really makes it all worse, right? Because the more variables we add, the more likely we add random and spurious correlations, even if all of these variables come from our scientific background or from the background of the domain we are interested in, right? But variables can behave in various ways, and if we don't need to just understand the variables, we also need to understand their correlations with our domain expertise. And adding these automatic ways, although it's frequently done, really harms building a good model. One other issue that you need to keep in mind is data quality, right? We've already said that machine learning learns from the data, and the data needs to be relevant, but it also needs to be correct. So typically there are many issues that you need to take care of. There may be missing values, wrong true values like wrong labels, wrong values in the features, outliers, or just different representations like true, or number one, right? Variables get reused with different meanings. That also happens in practice a lot. Right. Also, is the ground truth correct or not? Right? Defining labels should be simple. We know what it is, cat or dog. In this example, it's quite simple. However, you can find many examples where it's not quite so simple, like kitten or ice cream, parrot or guacamole, sheepdog or mob, right? Some of those are very tricky to tell apart. So that means in addition to all those data quality issues that we will also have data quality issues with the ground truth. There's very little around it apart from putting in lots of work and cleaning up the data, and experience shows that the more time you spend on cleaning up the data, the better the machine learning model comes, and it's often cleaning up the data brings more performance benefits than making the model more complex. And it's also in our scientific approaches, we fall into the same category, right? So there are well-known damage types, for example, that we can observe in electron microscope images, and you have the textbook cases which are very clear, and this is what's typically discussed in the lectures, of course. But if you then look at real samples, you will find these clear textbook examples, but you will also find a lot of border cases, right? So this was a survey taken in some lecture and say, what is it, right? Based on what you've learned so far. And you can see from the animation, right? Most people are really not quite sure, and this is not because they haven't understood what these different damage types are. It's very ambiguous and very difficult to decide. And that becomes an issue then when we define a training data set, because if you want to train a network, for example, on these kind of data, you need to assign one ground truth label to it. And of course, you can easily make a mistake without intending, of course, to do so. So building a large training data set, you need to add ground truth to each label, but it's very difficult for these non-clear-cut cases. Right? The bright side of this is that building such a training data set often leads to new insights about the scientific part of it, and that in itself is a process that is very valuable. One way to make sure that we learn correctly is to have test, train and validation samples. Right? Of course we want to use all our data, but then we cannot evaluate our performance independently. What we typically do is to split it into training and test data. 80% and 20% is a common value. Like for example, we have two classes, and we take the test data and the training data, and then we have an independent sample that we can verify our machine learning model with. Think about challenges. What could possibly go wrong here, or what are challenges that we need to address? So first of all, the test data may be too small, and that means it's not representative. For example, we also may have rare events, so they must be both in the training and in the test sample. That means we can't just randomly assign them. We actually need to look for these rare events and make sure that we have them both in the training and in the test data. And in particular, if you have very little data, we don't want to sacrifice, shall we say, 20% of it. It's quite a substantial part. If we have really only very little data and it's very costly or impossible to get more data, sacrificing 20% is quite an issue. So what we could do in this case is cross-validation, right? So we have multiple trainings and we do different splits of the training data, right? So for example, here we have an example of fourfold cross-validation, right? So we repeat the whole training process with different test and training data 4 times, but we have a different split of the data. However, that doesn't work in all cases because here the assumption is that data can be split randomly. That means we have independent events. We've already discussed that this is challenging if we have rare events, because then we can't really do this, but it doesn't work at all if we have events that are autocorrelated, like we have in repeated measurements of a sensor time series data, right? If we have sequence data, anything that goes where the order of events matter, like sensor data of our experiments, videos, time series, and so on. One approach here is to split into successive but ordered windows. Then we take different kinds of data sets into account. Now, as a best practice, what can we do about features? Use domain knowledge to create good features. Don't just add everything and anything. Right? Understand the correlations between the features and the labels, but also importantly between all the feature variables that you devise. Try to find causal features, and by that we mean features where you know from your domain background that they are relevant to the problem at hand. Invest in data quality, because this really brings the most performance boost. It's sort of a boring task if you want, but but your model really benefits from that. Understand where data quality issues come from. Don't just delete data with missing values. They might be missing for a reason. For example, that a given sensor always fails in certain circumstances, and you need to address that. Also, by deleting parts of the data, you may or may not introduce a bias. Also, don't just remove outliers, right? For example, they can become about mistakes in the data acquisition and data handling. Okay, fine, then you can remove them because they were genuine mistakes. But they could be genuine but rare events, right? So these are the events you want to keep, even if they are outliers, but they're by definition outliers because you have a rare event. Also, invest time in storing data properly. You need to decide what that means for your use case, because the technicalities will make your life easier later. Just in training sample, we've touched upon evaluate your model on an independent sample, right? Define and set this aside before working, if possible, in sufficient data, and be careful with sequence data. You often also want to have a third data sample because many models depend on further hyperparameters that need to be tuned, like the learning speed or whatever you need to do when you define your features. Right? A validation sample would ideally be a third sample on which you tune these parameters, but the challenge is that you rarely have enough data, especially of rare events, to have 3 independent samples, so you need to be careful on how you deal with that. Now, let's come to applications, and we learn from machine learning. One of the things we test upon in statistics is hypothesis testing, or as we do it in machine learning classification. So hypothesis here is a statement. We want to use data to verify or falsify. Like is the coin unbiased? Is algorithm A better than algorithm B? Is a dog? Does the medicine work? And so on. And classically we have the null hypothesis, the status quo. For example, the medicine does not work, and H1 is the alternative hypothesis. This is what we want to test. The medicine, for example, does work. So how do we do this in machine learning? Let's take a simple case of two classes, and we transform our data into probability for each class. This is called test statistics. In statistics, we build this with different methods. Right? In machine learning, we use the machine learning algorithm to create such a test statistic for us. So we, we feed in the tabular data or the images or whatever data we have into the algorithm, and out comes our test statistics. And of course, in the best case, we would have our two classes, the medicine works or doesn't work, and these classes will be well separated, so it's easy to tell them apart. Of course, that would be great, right? So all true negatives are to the left, all true positives are to the right, and our machine learning algorithm does this perfectly. We've seen already this kind of image and learning from data, right? Classes can be very difficult to distinguish. This doesn't apply just in defining the labels, but it also then means that it's very difficult to think about the predictions, right? So we expect that these distributions and probability of assignment of class 1 and 2 will overlap, right? So we need to quantify a prediction as probabilities. So that means that we need to be able to tell how sure we are of our result. It's not enough to just say 1 or 2 or 0 and 1, class A and B or whatever. When it comes out of a machine learning predictor, we need our classification result as a probability. And this is what we've already discussed in hypothesis testing. We assume so far a Gaussian, but more realistic, we have two distributions, one where the null hypothesis is true and one for the alternative, or for class 1 and for class 2, or class A and class B. Right, so how do we decide them? And then we need to think about our errors of first kind or type 1 or type 2 errors again, and which hurts us more. Right. So we have now the realistic case that the machine learning algorithm says true or false or positive, negative, class A, class B, however you label it. And then you can build such a confusion matrix where you have the positively predicted, the negatively predicted, or class A, class B, and the true positives and the true negatives. And of course we want to be on the diagonal, but we do have this false assignment because it's in many cases not clear which class it really is. So we express everything in probabilities, and you need to decide if the false negatives and or the false positives hurt you more, and then make your choice accordingly. You can then use these to define a number of metrics, right? So for example, the true positive rate, the accuracy and precision, these are frequently used, but you can see that there are a number of other metrics, and just having many metrics doesn't help you, because when you discuss your application, you need to evaluate which is the most relevant metric for your specific case, right? It doesn't help to just list all of them and then list them, for example, in your final result. You need to be able to discuss them and say, for this application scenario, the accuracy, for example, is most relevant because, or the precision, or whatever it is. One other way you can evaluate prediction is the ROC curve, right? So we have the prediction as a probability, and then you define which threshold is best for you. So that depends again on the application, right? As we said, do false positives or false negatives hurt you more? But what this ROC curve, the illustration, helps you with is to look at how well does the model perform in general, and how does it depend on the cutoff value of the predicted probability. The ideal case is the upper left-hand corner, false positive rate 0, true positive rate 100%, and the better the model is, the closer you come along the y-axis to this point in the upper left-hand corner and go to the right. The diagonal line and the triangle below it says that your model is worse than guessing. Right? And then by stepping through the prediction values for a predicted probability of your model, you can go through and then see how it behaves and define a suitable point. We've discussed mainly two classes, class A and B, class 0 and 1, and so on. If you have multiple classes, you can do the same formalism, but you need to now normalize the output for multiple classes. So say you have 5 classes, right? And then this is done using the softmax approach. It is not really a probability in the sense it just looks like one. It sums to 1, so this is why it looks like a probability, but it is not properly calibrated, right? But it does help you to set a threshold, because now we have multiple classes and each value is such that it's in the range of 0 to 1. This also then allows you to extend the confusion matrix to n classes. And briefly, let's discuss regression, right? We already said in the statistics part that mapping a set of data points to a value, this is what we essentially do in regression, right? So we have our prediction y hat, that's some sort of function of depending on some parameters and the input values x. The typical simplification is that we predict just one value, and this is the expectation value given the input data. And in linear regression, right, how do we choose this functionality? In linear regression, we just take some sort of coefficients over all of these feature variables. Of course, you can do more complex things, and this is also what machine learning then does for us. We've discussed about regularization, right? Instead of having a too flexible model, we add some penalty to it, and we have multiple choices of penalties. And if we want to go beyond simple regression, right, so we fit a single line with a true model, meaning we have a single line y equals mx plus b, and the variance is just due to noise. And then this sort of works. Linear regression gives us the mean. However, we know that variables follow a probability distribution, right? So this is one of the key things that we learned about statistics, right? So simple regression means we estimate the mean, but typically this is not sufficient, especially if we have asymmetric distributions. What we can do is to have quantile regression. So there are two approaches to this. Either we know the underlying probability density distribution under which the variable that we want to predict is distributed, right? Then we can estimate the parameters of this distribution with individual models. Or we can take what's called a quantile regression. This is similar to linear regression, but for specific quantiles, and we can capture the behavior of the distribution this way. Right. In linear regression, we said the mean is the estimator, and in quantile regression, we take a specific quantile. Of course, which quantile do we want to use? No answer fits everything, right? So for example, if you have a shop, you want to have a high product availability, you want to be able to model the tails, the high tails of the distribution. If you have predictive maintenance, reliability engineering, you want to model a low probability of failure, you really need to decide on your application scenario what you need to model. Then, most regression tasks typically predict a single number, right? Naively with a simple linear regression, right? This is the mean. This is also what most machine learning models then do, or we have a specific choice in quantile regression. Now, if we want to evaluate this, how do we go? We could say we define the prediction error, which is the difference between our true known value, the label, right, in our test data, and the prediction. That sounds sensible. However, we're dealing with distributions, right? So even if the model is perfect, we can see that the prediction may be very different from the true value just because we're now dealing with random variables. So in general, we can't expect this equation y equals y hat or the true value equals the prediction. And the more volatility or the higher the variance of the distribution of the random variable that describes our prediction, the worse this gets. So what is commonly done in regression? So let's compare single numbers, right? So in the mean squared errors is one of the popular metrics and has a strong emphasis on points where y is far away from y hat. So it penalizes where the ground truth from the test data is far away from the prediction because of the square. That sounds useful, but we've just seen in distributions with high volatility or high variance, this becomes a problem because the prediction is okay, it's just that the distribution is so wide. The mean absolute deviation does take the absolute value instead of the square. This is a bit more robust towards these kind of outliers, and if you need to compare numbers, it's a good default choice. Let's discuss this in a toy example and see the effect of these metrics. So say we have a very, very simple model. We just generate a prediction by taking the true value and add some random Gaussian noise to this. So essentially our true value or the prediction is the same but a bit smeared out, right? So we put the prediction on the x-axis and the true value on the y-axis. And you can see it's essentially a straight line, but because we added noise to it, it's sort of spread out and blurred out. Now let's compare the performance of mean squared error versus MAD. Let's take a sample size of 500 events in our test data and we compute the mean squared error and the MAD. And now we normalize the values so that if we have now all 500 values taken into account, each metric is divided by the final value, so we have a final value of 1. Now we order the mean squared value a metric by these differences between prediction and true value squared, and for the MAD we do this by the absolute value. And now we visualize how many events contribute to the metric. So remember, if we have all 500 taken into account, we end up at 1. This is what the top right corner of the lower plot looks like. And then we follow, if we add 1 event, 10 events, 50 events, and so on, and see what kind of fraction we have. And we can see that the MSE rises quite rapidly and the MAD a lot slower. So for example, if we take 80% of the final value of the metric, for the MSE, we see that we've evaluated roughly 180 of our 500 events in the test sample, whereas for the MAD, we need to go at least above 300. Right? So that means that the wider our variance is, the fewer actual test cases make it into the value itself. Right? And this is of course a problem, because when we assume that we evaluate all 500, right, depending on the variance of our random variable that we want to predict, if this is very large, we only have a few values that may even be perfectly alright, but we don't see where the evaluation has a problem. There are a few other metrics like the mean absolute percentage error. This looks like the MAD but divided by the true value. That of course means that the true value needs to be greater than 0 for all of them. And you may introduce a large bias for small values. The MASE, the mean absolute scaled error, is essentially the MAD versus the MAD of a naive prediction, and of course that can lead to large biases depending on how you normalize this with a naive model. You already know that the naive model isn't good enough in many cases, otherwise you wouldn't have a different model. What can you do? One approach is to take the diagonal plot and expect that the prediction is a good estimate of the true value for all values, right? So ideally we want to have that all y pairs should lie on a diagonal and they should scatter around the diagonal but in an unbiased way. So this is okay. If you have a systematic deviation from this red line, then you have a problem. So this plot allows you to identify regions where the model doesn't perform quite well. So let's go back to our previous example, right? So we have a prediction and the true value, and the only way that we modify the true value is by adding some Gaussian noise to this. How do you create the plot? You split the x-axis, our prediction, in n bins. Now we always put the prediction on the x-axis and we put it into n bins, and how many you have, and if they're symmetric or asymmetric, you need to decide on the distribution of the data. And in each bin you calculate the mean of the true values of your the true values and a dispersion parameter like the standard deviation, the variance, and so on, depends on what you use. And then all points should be statistically compatible with the diagonal. Now in our simple case here, we see that this is not quite the case. Remember that our prediction was just the true value plus some noise. That seems like a perfect prediction, but why do we see these problematic areas now? Now, it's to do with the edges. So for example, we have very small error bars. That means that there are very few events. And that means that the calculation of the variance becomes unreliable. but also you can see a systematic trend. On the left part of the plot it goes up, and on the right part it goes down. And why is that? Well, the noise is always wider, right? So the y values always get shifted outward but never back, right? So you can compare our sort of prediction distribution, the blue one with the true one, and it's wider, and this is why the plot has this problem. So the profile plot is quite sensitive to any problems that you will have in regression problems. Remember that the prediction is a random variable, right? So it implies that it follows a given probability distribution, and we need to predict a distribution, not just a number. Predict either the parameters of a known or assumed distribution, right? In many cases you do know this from your domain knowledge, or do some quantile regression interpolation, then you can build some sort of empirical probability distribution. How do we have further ways of evaluating this? So a random variable distributed according to the CDF, the cumulative distribution of another random variable, is uniformly distributed between 0 and 1. So this is another way of evaluating if your prediction is good. But what does this mean? This brings us to the theorem of the probability integral transform. So if we have a sample from a random variable distributed according to the true probability distribution, we can transform it into a sample following a uniform distribution. What does that mean, and how do we use this? Let's start by going to the basics. The cumulative distribution is the probability that the variable has a smaller value than x. It's essentially the integral, right? There's now an example shown for a Gaussian distribution on the right hand side, and you can see the probability distribution, this is our Gaussian, and the cumulative distribution is essentially the area under that distribution, right? Now, if this cumulative distribution is continuous and strictly increasing, then that means that the inverse always exists. Right? So go back to the previous slide. Right? You can see this is rising, and you can map one to the other because the area, depending on where you are in the cumulative distribution, that defines where you are in the probability distribution. So you can define this inverse, right? And you have unique value for each value in 0 and 1. So this means we can now define a new random variable as f of x, the cumulative distribution, and then the inverse exists. Now here's a little proof that you can go through. And if we do this new variable transformation, the new variable is uniformly distributed on 0 and 1, right? Assuming that we have the correct underlying distribution. So how does that help us? Now we can apply this power integral transformation if we know that we have the right underlying distribution, for example, as our model choice, in this case the Gaussian, and we estimate the model parameters correctly. The distribution of the observed CDF values of the cumulative distribution is uniform regardless of the choice of distribution. Right? Now here we do take a Gaussian example, but it works for any, as long as we can satisfy the assumptions. So if we do this, the observed CDF values, right, we generate samples according to the normal distribution, apply this on the sample, and we see that we have the uniform distribution. Okay, fine. So how does this help us? Right, it works for asymmetric distributions, like take, for example, this distribution, which has a long tail to the right-hand side, and the cumulative distribution is shown here. Right? It's the same distribution for the generation of the sample and applying the CDF, and again, we have a uniform distribution. Good. Now, we generate the sample with one distribution and one set of parameters and apply the cumulative distribution with the same distribution but slightly different parameters. Now it's no longer uniform, so that means either the choice of the model is wrong or we've estimated the model parameters not correctly. Right? So if we end up after this power integral transform with a distribution that is no longer uniform, we know that something is wrong and need to investigate further. So, as you've seen, evaluating regressions is full of pitfalls, right? Metrics, the most commonly used metrics, like the MSE, MID, MAP, and so on, they are for single numbers, and they don't consider the variance, and they don't take into account that we really need to do with probability distributions. A diagonal plot helps us to identify regions with bad predictions, but also relies on single numbers, right? Ideally, we need to predict the predictions, and the power integral transform allows us to check the model choices and calibrations. So, key takeaways. Machine learning allows us to learn from data, but we've seen it's not without obstacles. Data quality is a major issue, both for the features and the labels, and investing time in data quality is maybe not as glamorous as developing a new machine learning model, but it has large benefits. And then we can either think about classification and regression. Right? Classification we can also relabel as hypothesis testing with machine learning, if you like, if you think more in statistics terms, right? But we do need to think in terms of random variables and probabilities, even with the use of machine learning. And choosing evaluation metrics is difficult and relies a lot on domain knowledge about your specific application use case. For regression problems, even worse, because most approaches that you will find do not capture the complexity of that issue, so you need to think again in terms of random variables and probabilities, and most regression models you will find don't handle this kind of complexity. And as we've just seen, be even more careful with your choice of evaluation metrics.